Alright, ladies and gentlemen, this is going to be the next video on Gay-Lussac's law. And we're going to be delving into what the law is and then how to do the calculations associated with it. So let's go through and do this next video. So what is Gay-Lussac's law? Well, Gay-Lussac's law states that if we maintain a constant volume and a constant amount of gas, the pressure will increase if the temperature also rises. So if we're looking at this, the pressure is directly related or directly proportional to the temperature in Kelvin. And here's a picture of Gay-Lussac, and his discovery has changed the way that we understand pressure and temperature. So let's say we have these two containers here with the same particles of gas, same number, same weight. If I go through and heat this first container up to 200 degrees Kelvin, it's going to maintain a pressure of 1 atmosphere. And then if I go through and heat up this second container to a temperature of 400 degrees Kelvin, well, it's going to reach a pressure of 2 atmospheres. Well, why is that? Well, the temperature is related to the movement of the particles. The particles in this container are moving slower, so they're exerting less force in the actual container and then exerting less force on the particles themselves. Now this gas, since it's heated up a lot more, well, they're exerting more forces on the container and a larger force on the actual particles themselves. So therefore, because temperature is really a measurement of the movement of the particles and the energy the particles has, well, the pressure is going to increase. So if we're looking at the formula here, well, it's going to be P1 divided by T1 is equal to P2 divided by T2. So our initial pressure, well, this is what P1 is going to stand for. And our initial temperature is going to be what T1 stands for. Now pressure 2, this is our final pressure. And then our final pressure is going to, or our final temperature is going to be T2. So it's P1 divided by T1 is equal to P2 divided by T2. This is the formula for when we go through and apply this to our calculations. So let's go through and delve into our next problem. We're being asked to calculate the final pressure for a gas with an initial pressure of 1200 torr at 125 degrees Kelvin that is cooled to 1 degree Kelvin. We're working with Kelvin and we'll explain this in class a little bit. So our formula here is going to be P1 over T1 is equal to P2 over T2. Now here's the thing. We are going through and solving for our P2. Solving for our final pressure. So let's go through and punch this into our formula. We're going to take 1200 torr, which is going to be our initial pressure, divided by 125 degrees Kelvin, which is our initial temperature. We'll go through, we're solving for P2, so I'll put in P2 here. And then our final temperature, we cooled it down to 1 degree Kelvin, so almost to absolute zero. So the question is, what will this be? Well, I'll go through and do 1200 divided by 125, and then I'll multiply both sides by 1 degree Kelvin. So we'll cancel degree Kelvin, my Kelvins cancel. We get our final pressure in torr, so we'll do 1200 on the calculator. 1200 divided by 125 equals 9.6 multiplied by 1. So our final torr, P2, should be equal to 9.6 torr. Remember, they're directly proportional. As my pressure goes down, so should my temperature. And as my temperature goes down, T, so should my pressure. Let's go through and take a look at this one. Calculate the final pressure for a gas with an initial pressure of 1.5 atm atmospheres at 12 degrees Kelvin that is heated to 35 degrees Kelvin. We're going to do P1 over T1 is equal to P2 over T2. Again, we're calculating for P2. This is what we are solving. This is what we are solving for. So let's go through and do this one together. So, initial pressure, 1.5 atm divided by, well, our initial temperature is 12 degrees Kelvin. We set this equal to, well, we're solving for P2, divided by 35 degrees Kelvin. So we're heating it, so our pressure should go up. Multiply both sides by 35 degrees Kelvin. This will cancel. Multiply this side, 35 degrees Kelvin. Kelvins cancel. So do 1.5 divided by 12 It's going to be equal to 0.125. And we'll multiply that by 35. Well, did our pressure go up? Well, sure. And that makes sense. Pressure went up to 4.375 atm, atmospheres here. So remember, as our temperature goes up, well, so should our pressure. So this one makes sense because we went through and heated it. So again, we're calculating the final pressure for a gas with an initial pressure of 1.20 atmospheres, 75 degrees Kelvin, and we are cooling it down to 12 degree Kelvin. P1 T1 is equal to P2 2. Let's go through and do this one together. Well, P1, what's our initial pressure? 1.20 atmospheres. Remember, we are solving for this one here. We're going to divide that by our initial temperature, which is 75 degrees Kelvin. Solving for P2. Then we'll go through 12 degree Kelvin. Multiply both sides by 12 degree Kelvin. That will cancel. 12 degree Kelvin. Kelvins cancel. Left with atmospheres. So 1.20 divided by 75 multiplied by 12. Final answer here, pressure 2. Well, that should be approximately 0.192 atmospheres. So, does this make sense? We cooled it. Our temperature went down, so therefore our pressure must also go down. And it's 0.192 atmospheres. All right, and then our last one here, calculate the final pressure for a gas with an initial pressure of 780 torr at 84 degree Kelvin that we are heating up to 220 degree Kelvin. P1 T1 is equal to P2 divided by T2. Again, we are solving for P2. We will do more problems where we solve for the other variables. Let's go through. Initial pressure, 780 torr with our initial temperature of 84 degree Kelvin. Set this equal to solving for P2, and we're heating this up to 220 degree Kelvin. So our temperature, remember, we're heating this, increased, so therefore our pressure must also increase. So P2 must be greater than 780. Multiply both sides by 220 degrees Kelvin. This will cancel on this side. We will multiply this by 220 degree Kelvin. Kelvins cancels out. Well, we're going to get a value for our P2 of a pressure of 2042 torr. This is going to be our pressure value for torr here. So this is going to be the end of the video.